Alrighty, so with this video we will start talking about the special theory of relativity. Now, first thing to note is that relativity is a fairly old concept. Of course, the original version of relativity, which is the version we know of for our everyday lives, goes something like this. Say you are sitting on a bench, and you're watching the outside world, you're looking at things, and you notice an event happens. So firstly, these are your coordinates. Let's say this is X, and this is Y. Your coordinate frame, your reference frame, I'm going to call S. That is to say, your coordinate system, we'll call S. That way, when we have a different observer who maybe is moving relative to you or is not moving relative to you, they will have their own reference frame, their own coordinate system that they'll measure things, and we'll label it something else. So for you, you're sitting here at the origin on your park bench, and you're looking around, and maybe you see a squirrel or something climb a tree, and you see that event happen right over here. Okay, so something happens right there. You would say that this event occurred a distance, let's say X, from where you're sitting. Right? You're sitting on the bench, you see the squirrel climb the tree, and you measure the distance from you to the tree, and you find it's 10 meters or whatever it is. Fine. Now let's say someone else maybe they're jogging along the path in this park, and they also see the squirrel climb the tree. So they're moving relative to you. I will label this with a different color. They have their own coordinate system, and maybe their coordinate system looks like this. So their coordinate system I'll call S prime. They, of course, are sitting at their origin, and their axes I'm going to label X prime and Y prime. Okay? So you have your coordinate system, they have their coordinate system. Every single observer has their own coordinate system relative to them because, of course, if you say, hey, where did you see that thing happen? You measure it relative to where you were. You say, oh, it was 20 feet away from me. You don't say it was 20 feet away from that other observer over there. Who cares what their observation is? I'm talking about you. So their reference frame, their coordinate system, is currently moving because they're jogging along the path, and they're moving, let's say, with a speed u. Okay, so they have the speed of the primed observer. So they're moving off to the right with speed u, and so when they measure where this particular event occurred, the squirrel going up the tree, they would measure a distance from here to here as X prime from where they are. Okay, so maybe you're sitting on your bench, here comes the jogger. Right when he passes by you, you look at your watch, you see what time it is, and then you look up and you find the squirrel going up the tree, some distance X away. While that was occurring, this jogger was running past you with speed u, and they also looked at their watch as soon as they happened to pass you, and then they look up and look at the squirrel, and by the time they see the squirrel, they have moved past you a certain distance. Of course, the distance they moved is the speed they're moving times the time it takes for them to finally look up and look at the squirrel. So we have two different observers measuring the same event occur at a particular location in space. One person says that location happened at, so the S guy, you on the bench, they say this event occurred at location X at the time T. The primed person, the person jogging past you, they would say, well, I agree this event happened at time T, However, when I measured how far away it was, I found it to be at x prime. Now, this isn't strange, of course. There's nothing weird about this. The person moved past you. So obviously, when they measure the distance to where the squirrel was, it's a different distance than where yours was. Now, if we want to relate the two, we would say that the jogger, their position, that is to say how far away the squirrel is relative to them, is going to be, well, this x prime from here to here is, of course, the full x minus the distance they traveled, this distance right here, in the time as they were moving for him to see this squirrel. So it would be x minus u times t. Of course, makes perfect sense. You're moving with a certain, or they're moving with a certain speed, so they're going to be closer to this event happening by the time y'all both look at it. And he's going to be closer by an amount proportional to the speed they're moving. Now, the fact that they both agree on when this event occurred, when did the squirrel go up the tree? Well, it happened at 2:57 a.m. or whatever it is. So it's t prime is just equal to t. And then, of course, the other, if we want to talk about the fact that this coordinate system has 3 spatial dimensions and 1 of time, then, of course, there's also the y direction and the z direction. But given that the jogger's not climbing a hill or going down stairs or something like that, they're just jogging on a straight path, then y'all both would agree on the height and the depth of this event. So the only change is the change in the position measured from the S prime frame, that is the jogger's reference, to your reference frame. But you agree, yeah, that's the same location in space. It's just that because you were moving relative to me, you got closer to the event in this time t than I was. That's relativity. This is what Isaac Newton believed. This is what everybody believed. And in fact, we call this Galilean relativity. And all Galilean relativity says is that everybody agrees on when an event occurs, but people will disagree where, only in the sense of the actual coordinates, the actual location, you would say, is going to be a different number relative to someone who's moving compared to you, relative to you. But that's only because they're moving relative to you. In the actual absolute space, it's the same location. It's just I say it was 3 meters away, you say it was 5 meters away. But of course, it's the same location. It's just I got closer. Galilean relativity, this is what our everyday experience tells us. And in fact, we could go further. We could say, well, look, what would happen, for instance, if you're on some train, or let's say a person is on a train, they're standing on the top up here, and they're holding a ball. And so that person, he's just standing on top of this train car. We don't know if it's moving or not. It doesn't really matter. He's standing on the top of it. So relative to him, the train's not moving. He's just standing on this car. He throws the ball, and let's say he could throw the ball 100 meters per second. Okay, just to give, obviously, fake numbers, but clean numbers. So the velocity of the ball relative to this person who's standing on this train car is 100. No big deal. And if you, down here, as an observer, are looking at this, and let's say the car is not moving, when you look at how fast the ball moves, of course, you're going to find it's moving at 100 as well. However, if this train car now happens to be moving with some speed, let's say it's moving with a speed of 200 meters per second, then to the person on the train car, let's say they're not looking outside, they're not looking at the trees, anything like that. All they're looking at is on their train car, The floor isn't moving. They're standing on top of this car. The car's not moving relative to them. So when they throw their ball, the ball leaves their hand at 100 meters per second. However, to you, as an observer from the outside, not on this train car, you're watching the train car pass by. Of course, you say, well, the train's moving at 200 meters per second, and there's some dude standing on top of the train car. So the guy is moving at 200 meters per second as well. Then the guy throws this ball, and because he threw it 100 meters per second relative to himself, that is, it left his hand at 100, but he's already moving 200, you would find this person's speed, or the ball's speed, to be 300. That is to say, the speed of the car plus however fast the ball was moving relative to the car itself. Okay? Again, Galilean relativity, this makes perfect sense. You're in a car, or let's say you're in a bus, standing in a bus, the bus is moving at 35 miles per hour, you jump, nothing happens, right? You just jump up and land back down again on the ground. You can't tell other than in true reality. You could feel the bumps, you can look at the trees moving by you, the lines on the road, you can see all these pieces of evidence that you're moving. However, if this was a purely flat ground, and you couldn't look out the windows were covered up, you would not be able to tell inside of this bus that the bus is moving. You just feel like you're standing in a bus that's just sitting there. Same way if you're in an elevator. When you start an elevator, of course, you feel the elevator start to move, but then once it's moving, let's say you're in a big skyscraper, once the elevator starts moving, all of a sudden you can't really tell if the elevator's still moving or not, other than by the sounds and things like this. It's only when these things change their speed, that as they accelerate, that you can see these effects. So to the person in the bus, even though the bus may be moving or may not be moving, they have no idea. So they would say, no, the bus isn't moving, it's at rest. And so I do all these physics experiments, and I find all of Newtonian physics works. Right? I mess with springs, I do a pendulum, I hit billiard balls around, whatever it is. All the experiments that I would test physics from will work perfectly fine in that environment, even though that environment, the lab, is on a train car that's moving relative to someone outside the train. This is a very, very important phenomenon, that the laws of physics, Newtonian laws, but the laws of physics generally, the universe doesn't care about Isaac Newton, so the laws of physics don't care whether you're moving or not. It would be weird, let's say, let's say you're playing darts, you know when you throw this dart at this angle with this speed, it's going to land in the triple 20 zone or whatever. Now, if you're in an elevator, or get out of the elevator, let's say you're on a bus, and the bus is moving at a constant speed of 35 miles per hour, well, it better be true that when you throw the dart exactly the same way, it should go exactly the same location. Because everything in this bus, the air, the dart in your hand itself, everything is moving with the bus at the same speed. And so obviously you should get the same results. It would be weird if it didn't. If you were on this bus and you tried to throw the dart, and all of a sudden the dart did something really strange. It didn't move like you thought it would. And in fact, that'd be pretty bad, because even when you're in a stationary lab sitting in a building, that lab is still moving, because we're on the planet Earth, and the planet Earth is rotating, it's revolving around the sun, the solar system is moving through the galaxy is moving through empty space. There's all this motion being involved here. And so if any relative motion would mess up the results you'd get from experiments, then we'd never be able to do any physics, because every result would depend on how you're moving at that exact time and place and all this kind of stuff. That's not what we see, though. What we see is that no matter how you're moving, as long as it's constant speed, so you're either not moving or you're moving with constant speed, then all the laws of physics work out and everybody agrees on them. Okay? This frame of reference is what we call an inertial reference frame. Now, this is a funny thing, inertial reference frames. How do we define what an inertial reference frame is? Well, an inertial reference frame is kind of cyclically defined. We say that an inertial reference frame is that frame of reference, that coordinate system, whereby the laws of physics work. That is, F equals ma is true. Newton's laws work out in inertial reference frame. And so, how do I know if it's an inertial reference frame? Well, the laws of physics work. However, in the definition of the laws of physics, we say, well, the laws of physics work if you're in an inertial reference frame. Well, that's a cyclic definition. I can't say this location is called this because that thing is true, and at the same time, I'm going to define this thing being true only in these particular locations. Well, yeah, obviously, you just defined the same thing twice. However, we kind of understand what we mean by it. And one of the ways of thinking about it that's really easy for now, without getting too messy about things, is just imagine an inertial reference frame is that frame where when you're measuring things and you're doing your experiments, your motion is not accelerated. That is to say, maybe you're moving, maybe you're not. But if you're moving, then you're moving at constant speed. You're not changing directions, you're not changing your speed. Okay? If that's true, then every single person that's in an inertial reference frame will agree with you on the results of your physical experiments. Okay, things work the way they should work. Now, here's the problem. This is all well and good, this Galilean relativity that I have over here. This works perfectly fine for most of physics we do, in every observation we make, for the most part, except one significant issue. And that issue is when we talk about electricity and magnetism. So, before Maxwell came along, basically everybody understood, and it was widely accepted, that all the laws of physics hold in these inertial reference frames, and thus, because of this, if you're in a location that's an inertial reference frame, you would have no way of telling whether your frame of reference is moving or not moving. That is to say, if you get on this bus or this train and you black out all the windows and the floor, the road is perfectly frictionless so you don't feel bumps, all these kind of theoretical ideas, if you're in this location and you know it's not moving because you just got on the car and it wasn't moving when you got on, and then you fall asleep, and then you wake up, whether the thing is moving or not, you won't be able to tell, and there's no experiment you can do to be able to figure out whether this train car is moving or not. As long as, if it is moving, it's constant speed. Okay? Now, of course, if this is a train car or a bus, and they slam on the brakes or they speed up, you could feel that. And because you could feel the acceleration or the deceleration, then obviously you could tell, I'm moving. However, if you're just going at constant speed and not changing directions, there's no way to tell. That is what was understood as basically a law. This is a postulate. It is true that all the laws of physics hold in an inertial reference frame, and thus you cannot tell, if you're in an inertial reference frame, whether that frame is moving or not moving. So two people that are moving relative to each other, without, outside context clues or something, would always assume it's the other person moving. If you're on, if you're on the Earth sitting here and there's a rocket flying by, you're like, hey, that rocket is moving past me with a certain speed. But the person on the rocket over here, they're just sitting there and they're looking out their window and they see all this space moving by them. They would say, no, that's not true. You on this planet happen to be moving past me. I'm just sitting in empty space. I cut my engines off. I'm not moving. Y'all are the ones that are moving. And it turns out that if this is true, this postulate, that all the laws of physics are the same in all inertial reference frame, then neither one is correct, and both are correct. The person on the planet obviously would assume, well, my planet's not the one that's moving, it's the rocket ship going past us. But why is that true? We know the planet's moving, we know the Earth is going around the sun, and we know the solar system is moving. So it might be that someone calculated that if I lift off with a rocket, go out into space, and then I do these kinds of thrusts with my engine, then I will stop and I will be in no motion relative to, let's say, the center of the galaxy. So to me, on this rocket ship, I'd say, no, I'm not moving. I made sure that my rocket is not moving relative to the center of the galaxy. And because of the natural motion of the galaxy and the natural motion of the solar system, y'all are the ones that are moving by me. And so that's the postulate, that this must be true, and there's no experiment you can do that could find out which one of you is right. Then Maxwell comes along and studies light and electricity and magnetism. And unfortunately, he comes up with a set of equations called Maxwell's equations that work very, very well and explain everything we want, except we run into a problem. And that problem is, in his equations, it is basically forced upon us from the mathematics that light always moves with speed c. And that c, of course, we're just going to use 3 times 10 to the 8 meters per second. But the equations of motion, or Maxwell's equations, naturally force this upon us. That light, being this excitation of the electromagnetic field, moves at the speed of light always. And now, if this is true, and we go back to our example of someone on the train car kind of a thing, then we could come up with an experiment where we would be able to tell we're moving, because let's say you're in this train car and you have a flashlight. So here's the train car, here's the person inside the train car, and they have a little flashlight here. And they're going to shine light. Of course, to the person in the car, the light's going to leave the flashlight with speed c. Okay? And then run into the wall on the other side. And then you, standing outside watching this occur, you say, okay, yeah, the person's in the train car, they shone the light moved with speed c towards the wall. But now, the same exact experiment, except now the train car is moving with speed c over 2. Very quick. And so you say, okay, well, what would happen? Well, to the person in the train car, of course, the speed of light is still the speed of light. The light's going to leave its flashlight at the speed c. Just like the person on top of the car, train with a ball, when they throw it, it still leaves their hand at the same speed. It's just relative to the person on the ground, it seems faster because it was already moving with the speed of the train before you gave it the extra speed of 100. So, person in the car shines the light leaves the flashlight, hits the wall at speed c. What does the person on the ground see? Well, if normal Galilean relativity is true, then what we should expect is the person on the ground, when they measure the speed of light, they would measure it to not be c, but c plus c over 2. So they would get 3c over 2 as the speed of the light after it leaves the flashlight. But this can't be true because Maxwell's equations say light's speed is always c. So if you measure the speed of light and it doesn't come out to be c, then you know something's moving here. We disagree on the speed of light, and since I know what the speed should be, the fact that I get a different result means you must be moving, and thus you could do some experiment to figure out which one is the correct one. Okay, well, okay, fine. That's the way it is. So what? You can say the same about sound, right? Sound moves with a certain speed in air, 343 meters per second. So someone in the train car, when they speak, they're going to speak the sound comes out of their mouth, goes to the other side of the room, moving through the air at speed 343, the velocity of sound. Person outside, they're looking, they say, okay, what's happening with the speed? They would measure whatever. But here's the difference. The difference is this. In the car, sound has to travel through something. Okay? It has to go through a medium. If you're just in empty space, sound doesn't exist because it's the pressure moving the molecules in the air or whatever medium we're talking about that creates the sound wave that we detect. So it's the air that's the medium through which sound will propagate. Well, the same is true, I would expect, for any wave. Water waves require water. Sound waves in a guitar string, you need the string itself. You always need some medium for waves to move through. Light, of course, is a wave. And so obviously light must need a medium as well. So with sound, we're not worried about the fact that this is weird for sound because sound has to go through a medium. And the reason the speed changes when you go from outside the train car to inside the train car is because the medium is moving with the train car. The air in the train is moving with the train. So we have an example of this wave will propagate through a medium, but the medium is moving with the location as well. Is this true about light? Is there a medium for light? And maybe that will overcome our little contradiction going on with two people seeing different values of the speed of light. And that's what the ether is all about. It was always thought that there is some weird medium that propagates all of space that we call the ether, and it's this medium that light can propagate through. We know something has to exist because it's not just that, oh, light just goes through air or water or glass or whatever, because what about the light coming from distant stars? Those distant stars are sending out light, it's getting to us, but it's going through a bunch of empty space. There's no air out there for the light to go through, there's no water. So how does the light get to us? If, like I said, if this was sound, obviously lots of sound is produced down in space. You have lots of explosions. You have the stars themselves are fusion reactions occurring constantly. So there's lots of sound being produced, but that sound never reaches anything because there's no medium through which this sound can propagate. Well, if light is getting to us, that means there must be something there for the light to propagate through. At least that's the thought. And so we don't know what it is. We're just going to give it a name. We call it ether. For whatever reason, we can't really detect it. We can't feel it. We can't see it. But it's some medium that must be there because light has to propagate through something. And so that's the thing we're going to call it. And so the question was, okay, well, if the ether exists, how are we moving relative to the ether? Because just like with anything, if light has to go through the ether, if the ether is moving, then the wave that's in this ether is moving with it. And so obviously, if you move relative to the medium through which a wave propagates, then that wave is going to have different speeds depending on how you're moving relative to it. If you have a water wave, it's moving through water, then obviously if you're in a boat moving towards the water, towards where the wave source is, then the wave comes at you faster than if you're moving away from the wave's source. So the same should be true about light. There's this, vast liquid or fluid that we call the ether, and it is that fluid that's going to be waving, causing light. Well, if we move towards the source, we're moving into the ether in that direction, then we would expect the light to move faster, and when we move away, it would move slower, or at least we would detect its speed as slower. And so that's what Michelson and Morley tried to do. Michelson and Morley did their experiment. What they did, it's basically an interferometer. If you have light gets sent, splits, some light goes this way, some light goes this way, and then depending on how you want to do it, you could put another mirror here and another mirror here that reflects the light back. And then you can detect things like interference patterns if the light moving this way took a longer time, if these lengths are the same, this is length L, this is length L. If the light moving in this direction has a different speed than this direction because of how you're moving in the ether, then when the light comes back to this location here and combines again, there's going to be interference patterns. And so you could deduce the difference in speed from this interference pattern and figure out, okay, we must have been moving this fast relative to the ether versus this fast, and so on. So they did it one day, and they found, in doing all their calculations and everything, the final result said the speed of light today is 3 times 10 to the 8th. Okay, obviously they had a much more accurate number, but just for the numbers' sake, I'm going to call it 3. I said, okay, well, either this is a huge coincidence that on the day I decide to do my experiment to measure the speed of light, I happen to get exactly the right theoretical value that would be true if I was not moving relative to the ether. So, of all the days, of all the time to go check the speed of light, I happen to check it when the ether's moving this way, and I happen to be moving in the same direction at the same speed. Okay? That might be true. I mean, who knows? It's fairly unlikely. So what other result could there be? Well, maybe there just isn't an ether. How would we be able to tell that, well, it's just a coincidence, we happen to measure right when we're moving in the same direction with the ether, versus the ether just doesn't exist, and so obviously the motion of the planet has nothing to do with anything. Well, one way of doing it is saying, okay, well, notice, here's the sun, here's the earth. When we measured, and the earth goes around the sun, let's say, when we measured, we were moving this direction, and we found that the speed of light is c, exactly what the theory says, so maybe it turns out that the ether is moving this way too with this exact same speed. Well, if we wait 6 months and come over here on the other side of my orbit, let's say the ether's still moving in the same direction. Why in the world would the ether all of a sudden change direction? It's a fundamental thing of the universe. So likely what's true is now that we're on this side and we're moving in this direction, we should be moving opposite to the direction of the ether, so we should get a different value when we do the experiment now. Because, yeah, it happened to be a coincidence, we were moving in the right direction the first time, but now there's no way we're still moving in the right direction, because we're in the opposite direction. And they do this experiment, and what do they find? Exactly the same number. No difference whatsoever. So this is very strange. How could it be that, on the one hand, all waves require a medium through which to propagate? However, we're getting experimental results that either something weird's going on, where the ether is always moving in the exact same direction as we're moving, or there's no either whatsoever. Well, obviously there were other arguments that were made, things like, maybe just like if you're in a bus, as the bus moves, the air is inside the bus also moving with the same speed, so maybe it's just that the ether outside of Earth is moving with some speed, but the Earth just happened to capture some ether in its atmosphere, and by gravity, and so as the Earth moves, it's kind of bringing its piece of the ether with it. And so, of course, it's always going to be in the same direction. Well, it turned out, through different arguments that that can't be true. It can't be true that that's the reason. There must be something else going on. And so this is where the big issue comes in. We have, on the one hand, all of physics seems to follow this rule of relativity that if you're in an inertial reference frame, there's no experiment you could do that would detect whether you're moving or something else is moving. Who's right in that respect? However, we do find that for light, this seems to follow. Every time we measure the speed of light, we always get the same result. So whether I'm the one moving or you're the one moving, doesn't matter, we get the same result. But that doesn't follow our intuition of normal relativity. Normal relativity would say, well, if the light is moving inside of the car, and a car is also moving, then the speed of light should be different. It should be bigger than or less than before, depending on the relative motion. So we have some weird issue going on here. And we know it's not because there's some ether that's being moved in the car as well. Okay? Somehow, two observers that are moving relative to each other would both find exactly the same speed. And that doesn't work for anything else. Anything else you do, one person throws the ball, they find it to be however fast they can throw. Person outside, watching this thing occur on the bus, is going to find the ball speed to be a different number because it's the sum of the speeds. But that's not true for light. And this is what special relativity is all about. This is where Einstein's genius comes in. Einstein, he says, okay, I'm going to make the assumption or the proposition that the original thought, that is to say, all physical experiments will give the same result if you're in an inertial reference frame, must be true. It must be fundamental to the universe. And thus, it must be true that no matter how you move, and this is experimentally verified, no matter how you move, you will always detect the same speed of light. Okay? So you won't be able to do an experiment with light and get out of the problem. Relativity is relativity. This will always happen. You will find the speed of light no matter how you move relative to someone else, and thus you still will not be able to tell if you're the one moving or they're the one moving. But in order for this to be true, then we have to dismantle some pretty significant things. How could it possibly be true that when you measure the speed of light inside your bus sitting here, you measure it to be c, and when I look at it, I should get 3 over 2 times c, but rather I get c as well? How can both of us measure the same thing, even though we're moving relative to each other, and get the same speed? Well, what he said was, maybe what's going on is that when there is this, let's say, this conspiracy at work by light, or by the universe itself, to force the fact that you can't detect a difference, and thus, when someone is moving relative to someone else, their measurement devices must change. That is to say, what they think of as a distance x is not quite the same as someone outside saying it's a distance x. Maybe their lengths are different or their times are different. So what he said is, look, either when you measure this light, you would measure a distance over time. How far did the light go? How long did it take? Right? That's what velocity is. Distance over time. When you measure the velocity and in your reference frame, you get x over t. Whereas someone else, when they measure the speed, they measure in their distance and their time. But you get the same exact thing. This is c and this is c. Well, the only way this can be true is, number one, x is the same as x prime and t is the same as t prime, but we know that's not true. So the only other thing is x and t versus x prime and t prime will change relative to each other. That is to say, when you measured the distance, maybe you measured it to be 3 meters, but when I measured it to be 5 meters. So your length was smaller. Or the time, when maybe you're following, at this point, the light was turned on, it moved this far, and at this point it hit the wall. So you measured the distance from here to be x, and the time it took was t. And then the other person was moving relative to you, they found it to be x prime as the distance, and when they measured the time, they found t prime as how long it took. Of course, normally we would say, well, t is the same as t prime, right? We both agree you turn on the flashlight at t equals 0 seconds, and we both agree that the light hit the wall after 2 seconds. However, for the purposes of generality, to find out what's really going on, because we got some weird crap happening, let's assume that t might be different than t prime. Maybe there's some factor that's not the same. Maybe for whatever reason, not only do lengths change, that is, how far you think something moved is different to how far I think it moves, but also time. Now, it might be, after doing the math, that no, t and t prime happen to be the same, or it might be different. We'll find out, but for now we're not going to make an upfront assumption that they must be the same. So what are we going to do? Let's remember our old Galilean transformation. We had x prime is x minus ut, if you remember. And of course, it's also true, if we just rearrange this a little bit, x is going to be x prime plus ut, right? That's our old Galilean transformation, our Galilean relativity transformation. If something's moving with speed u, then when it measures a particular location, it'll find it's the other guy's location minus how far I've moved because I'm moving at u. Right? If you remember, here's the car moving. It's going to move a distance from here to here, u times t, before it measures where this location is. So it's going to measure this x prime. That's how far away it is when it measures relative to the original x, right? Okay, so these are our Galilean transformations. Let's do this. Let's say, okay, in order for this speed of light issue to work, that is to say everybody gets the same speed when they measure it, well, that must mean that there's some factor that's going to change the lengths that I use to measure the speed. Again, the speed is distance over time, so if I'm going to measure the speed, I have to measure a distance over a certain period of time. Well, maybe somehow the universe changes your distances based on how you move. So what we're going to say is let x prime be this x minus ut, but I'm going to multiply it by some factor that may reduce the length. So maybe because you're moving at a speed u, the distance you measure is a fourth of the distance I would measure, or half the distance. So when you say it's a meter, I say it's 2 meters. Okay, this gamma would be the 2 or the 1/2 or whatever. And of course, the same must be true the other way around. Because if I say you're the one who's moving, and thus your stuff is what's weird, by relativity, the whole point of all of this, you equally can say the same thing about me. No, no, no. I'm not moving. You're the one who's moving. So your stuff is the one that's limited by this number gamma. So you would say, oh, x prime plus ut times gamma. Right? They're both true. I don't know if I'm moving. I'm going to assume I'm not, and you're the one who's moving. So your lengths are changed by this factor gamma. But you equally can say, no, you're the one who's moving, so it's your stuff that's changed by the factor gamma. Okay, well, fine. That's what we have. So let me write it here. X prime equals x minus ut times gamma. And x is x prime plus ut times gamma. And now what I'd like to do is figure out what is this gamma. And the way we're going to do it is let's consider this particular event occurring. So here's S coordinate system, X and Y. And then here's some moving guy's coordinate system, X prime and Y prime. And that's S prime. And we say, look, this guy's moving coordinate system, he's moving with speed u. When both coordinate systems happen to overlap, we looked at our time, and then we sent out a pulse of light. That light went all the way over here to this location right here. Okay? So to u in S, in the S reference frame, at t is equal to 0, you sent out the light. T seconds later, the light hit this other side of the wall or whatever it is. It went to this location X. So to your reference frame, this thing of light went X distance, which is how fast is the light moving? It's moving with speed c, and it took t seconds to do it. Okay. Now, to the primed coordinate system, what do they say? Well, to them, when they measure this, they find x prime, that is the distance from their origin to where the light occurred, or hit the wall, wherever the event occurred. They say, well, the light was sent right when we crossed our paths, right? And then some amount of time later, t prime, the light hit the wall. The light was moving. How fast was the light moving? And here's the critical part. This person also says the speed of light is c, not some other velocity. And so to them, their distance is x prime is ct prime. Okay, so how far away from their origin did the light hit the wall? X prime, what is that? It's ct prime. How far did it go in their amount of time? All right, now what we're going to do is let's take these two things here, our two Galilean transformations, and multiply them together. So we have x times x prime is equal to gamma squared times x times x prime is x prime. Then we've got minus u squared t squared. Then we have the cross terms plus x u t minus x prime u t. Okay. Now, what do we want to do? Let's try dividing everything by x prime. What do we get? 1 equals gamma squared times x prime over x prime is 1. Then we have minus u squared times t squared over x prime. Then we have x cancels x, and we get ut over x prime. Minus x prime cancels, and we get ut over x. All right, now what I'm going to do is look at this here. T squared over x prime. Let me call that t over x times t over x prime. Right? Same exact thing. And also look at this, and also look at this. From here, what do we know? Well, if I have t over x is equal to c, and from here I get t prime over x prime is equal to c. Oh, I made a mistake right here. I forgot this prime right there, and that prime would put a prime here, which is a prime here. Sorry. All right, so now when we look at this, each one of these t over x and t over x primes is a 1 over c, right? T prime over x prime gives me 1 over c, and t over x gives me 1 over c. So I could rewrite this 1 equals gamma squared times 1 minus u squared, and then t over x times t over x prime is 1 over c squared, so c squared like this. And then u times t prime over x prime, which is u over c, and this is also u over c, so these two things cancel. So I get this. Solving for gamma, I get gamma then is square root of 1 over 1 minus u squared over c squared. So now I have my factor. By how much will your length change when you go to measure things because you're moving at speed u? Your length will change by a factor gamma, which is this number here. Notice it's extremely small because c is a very large number and that's squared. U, the speed you move at, well, that's usually pretty small relative to the speed of light. And so this factor gamma is really, really close to 1. We're not really changing things on ordinary scales. It's not until your speed gets really close to the speed of light that this number is meaningful at all. That's why we don't see weird effects from relativity under normal circumstances. We have to get to extreme circumstances. But now we have something interesting. Now what we have is x prime is gamma times x minus ut, or if you want to write it out, it's x minus ut over square root 1 minus u squared over c squared. Okay, well, as I said before, it's equally likely that there's some issue with t as well. Why is it only x that's the problem? Maybe t is a problem too. So let's find out. By the way, we could also do x is equal to gamma times x prime plus ut prime. Let's find out what is the factor for t. Right? This is the factor for x. There's a gamma there. Let's now find out how does t change. So let me take x is equal to gamma times x prime plus ut prime. And what I'd like to do is find out about t prime. How does t prime change relative to t? This is a prime here. All right, well, all I have to do is take this x prime, plug it into there. And what do we get? I get x equals gamma times x prime, but x prime is gamma times x minus ut, right, plus ut prime. All right, let me multiply things out. I get x is equal to gamma squared x minus gamma squared ut plus gamma ut prime. All right. Now let's collect things together. I've got gamma ut prime equals x minus gamma squared x plus gamma squared ut. Okay. Solve for t prime. I get t prime equals 1 over gamma x over u. Oh, sorry. X over u. And I've got minus gamma x over u. And I've got plus gamma times t. All right, so now let me write it on the next page. I've got t prime equals, we have 1 over gamma x over u. Then we had minus gamma x over u plus gamma times t. All right, then let's factor out an x over u. In fact, a gamma times x over u times, let's make it a minus gamma times x over u times 1 minus 1 over gamma squared plus gamma times t, right? So I factored out an x over u and a gamma, so this becomes 1, this becomes 1 over gamma. So I've got gamma t minus gamma x over u times 1 minus, now what is 1 over gamma squared? Remember, gamma squared is the square root of 1 over blah, blah, blah. So 1 over that squared is just the 1 minus blah, blah, blah thing. So 1 plus u squared over c squared. Right? If gamma is the square root of 1 over 1 minus u squared over c squared, gamma squared is just that thing without the square root. And then 1 over this thing is just the denominator. And there's a negative there factored out. And so we get this. The 1 cancels the negative 1. And I have gamma times t minus gamma times x over u times u squared over c squared. All right, this u cancels one of these, and I have gamma t minus gamma x u over c squared, or t prime is gamma times t minus x times u over c squared. And now we have something super interesting. Here we found out that the time for one observer for an event to occur can be different from the time measured by another observer on pretty much everything about the action. Just one guy's moving with a speed. That's all that's happening. That's kind of weird. If you're on a bus and you're moving past and you watch a car crash happen in the intersection, and someone on the street was also looking and saw the car crash, then if your bus is moving fast enough, then you would say, oh, that car crashed at 3:05 p.m., exactly 10 seconds after we moved past that red light. But the person on the street would say, no, that's not true. When you pass that red light, that car crash happened 5 seconds or 20 seconds, whatever it happens to be. So not only does the space, the lengths measured by someone who's moving change, and not just because, well, I moved past the starting location, but rather the lengths actually change physically. Also is true the time. If you're moving, then you will disagree with someone who's not moving relative to you, or who is moving relative to you, I should say. If you're moving, someone moving relative to you will measure a different time than you do. Or another way of saying it is, if you're not moving and someone moves past you, then y'all will disagree on a time and the space. This is different from Galilean transformations. Galilean, only the spatial thing was there. But now both space and time. So now we have our official Lorentz transformations. We have the location, the position of an object according to a person moving relative to you. So we're going to assume you're not moving. You assume you're not moving. So for someone moving relative to you, they would say the place where this event occurred is equal to x minus ut over square root 1 minus u squared over c squared. They would say when it happened, t prime is t minus ux over c squared over square root of 1 minus u squared over c squared. And then the other ones are fairly easy. Y prime is the same as y. Obviously, nothing weird occurred up and down or back and front. If, however, the motion relative to each other was in all three directions instead of just along one axis, then there'd be some mix-ups going on here. But why do that when you always have the freedom, as a person solving a problem, of reorienting your coordinate system so that the motion is always along one axis? You could always do this. And thus, we just say it's along the x-axis. So these are your Lorentz transformations. Now, obviously, they're called Lorentz transformations, not Einstein transformations, because Lorentz was the one who did the math behind this. The mathematics was done before Einstein came around to use it. What made Einstein so genius was not that, oh, I came up with this mathematical model, but rather he knew, or he had the insight, to not be afraid to go down the road of, I'm going to make the postulate that this inertial reference frame idea, that the laws of physics are the same in every inertial reference frame, and I'm going to assume the universe conspires in such a way that there is never an experiment you could ever run that'll be able to determine who is officially the one that's moving and who is not. And I'm going to go with it, even though what it means is I have to get rid of this idea that space and time are in some sense fundamental to the universe. That is to say, there is some coordinate system out there and some clock that is the official clock of the universe, and everything else beats relative to it. No. If you're moving with a speed of half the speed of light relative to me, then there's nothing you could ever do that'll be able to determine that actually you were the one that was moving, not me. And in order for this to be true, then it must be true that not only does your measurement devices not work correctly, at least according to me, but your time itself is different. We can kind of accept spatial things for whatever reason, but it's the time that's very strange. And this isn't some weird effect about maybe it's the mechanism, maybe there's the problem of the tool. This is something that pops up in quantum mechanics a lot, like with the Heisenberg uncertainty principle. Oh, well, the reason you can't know the position and momentum of an object simultaneously is, to within perfect accuracy, is because in order to look at where the thing is, you have to shine light, and that light is powerful enough to move the object. Yes, that is true, but that's just a weakness of us as humans. That's not fundamentally true of the universe. There's nothing in the universe that says this electron does not have a position and a momentum. There's nothing in the universe that says, or that's exactly what it says. It's not that, you know what, it does have a position and momentum, it's just hard for you to find it. No, there's something fundamental about how things work, and it's confusing to us, and that's what makes things hard, because not because this is just the natural state of the universe, it's because we're not used to it and we don't have the language to describe it correctly. Well, the same is true here. It's not that it's difficult to do this, or it's our tools are the reasons. Maybe it's the way your watch works. When you move really quickly, the things have more resistance. There's nothing like that. It's a fundamental thing, and in fact, one of the examples of this that's very famous is the muon problem. The muon problem says this. Up in the atmosphere, so here's the Earth and here's the atmosphere. There's cosmic rays coming in, very, very high energetic particles from whatever, maybe supernova, maybe magnetrons, something out there. And when this high energy particle comes in and hits a piece of the atmosphere, it's so high energy that it creates new particles. One of these particles is a muon. And muons are, as you remember, a version of a lepton. It's like an electron but heavier. And we know that because it's heavier than the electron, it's not the fundamental one, so it's going to decay fairly quickly back down to an electron and some other stuff. And we know the lifetime of a muon. All muons of this type are identical, so they all have the same lifetime. And so what we would expect is, well, they should live for, I don't know, 10 to the minus 8 seconds or whatever it happens to be. And I know that the distance from where this muon was created all the way to the surface of the Earth where we can detect it is too far for the muon to get through at the speeds it can travel. That is, even if it traveled the speed of light, which it can't, it has to go slower, but even if it did, it wouldn't be able to reach us before it died. Yet we're observing them, we're measuring them. And the reason we're measuring them is because since these muons are traveling so quickly near the speed of light, their time literally slows down for them by this factor gamma so much that they think they're dying in the same amount of time, but to us, their time is slower, thus they're making it all the way down to the Earth. You say, well, wait, that's kind of weird. And yes, it is. It is very weird. In fact, I hear it a lot, and it's always a pet peeve of mine when you've got scientists who are all nonchalant and macho about things. Oh, there's nothing weird about quantum mechanics. Of course, it makes perfect sense. Well, everybody says it's weird and hard, and it's not. No, it is weird. Stop lying. It's weird. It's just that you know how to do the math. That's fine. But philosophically, what's happening is weird. And the same thing here. You're telling me that just by moving faster, not accelerating or anything, just by moving faster, your lifespan can be elongated relative to someone else. Your time literally changes. That's a very odd thing, but it is indeed true. But you say, well, maybe, how can that be? Well, what does the muon think? The muon says, look, I know I die, give it normal units. I'm going to die in 5 days, but the distance from the atmosphere down to the Earth, it would take me 10 days to get there. So I'm never going to reach the Earth, and then boom, he reaches the Earth. What does he think? You think, wait a second, how did I live long enough to get there? Well, here's the trick. To the muon, his time isn't different. Yes, it's true. He should die in 5 days. So how does he get down to the bottom? For him, it's his length has changed. When he measures the difference from the atmosphere to the ground, because he's moving so quickly, his lengths have contracted. Thus, when he measures the distance, it's not, 10 kilometers away. It's only 4 kilometers away. So the distance he has to travel is enough for his lifetime. So we don't have a contradiction. To us, not moving relative to the moving relative to the muon, we're the ones not moving, it's moving. We say, in order for it to reach the ground, which is this far away, he has to live this long, which is longer than his lifetime. Thus, his time slowed down. To the muon, he's like, no, there's nothing weird about me. I'm just sitting still. It's the Earth that's coming up towards me really quickly. And yes, I reached the bottom, not because I'm living longer. I'm living my normal lifetime, but rather because you're measuring the distance different. The distance from where I am to where the bottom of the Earth is, or the ground of the Earth, is only this big. You're saying it's that big when it's not. And both are true. It turns out you can't say the muon is right, and you can't say you as the observer is right. You're both right, and you're both wrong. That's what this relativity thing is. There's nothing you can do without things like accelerations and things like that that would allow you to detect the difference. Which one is the correct one? They're both correct. There is no final judge about motion. Which one's the relative motion stuff? So anyway, that's just an example that shows this time effect is not just some weird mechanical effect that's also just length contraction but happening in a watch or a clock. No, there's some fundamental aspect of time that's being changed because of your motion, and space as well. Okay, so that's Lorentz transformations. Next time we will go a little bit deeper. We'll talk about, well, if lengths can change and times change, then what happens to velocities? For instance, what happens in this example where I had the, way over here, the guy in a train car, in a bus, moving with speed c over 2, shines a light. The person on the outside, in our naive, normal Galilean transformation, would find the light should travel faster than the speed of light. But we know he doesn't. So then what is the mathematics that allows us to determine what this outside observer will actually see? What do they see the speed of light, the speed of that particular light beam to be? Or if it's not light, obviously he's going to see it to be c. But let's say instead of a flashlight, it was the ball. Someone throws a ball with a speed, 9/10 the speed of light, and this train is moving half the speed of light. Well, how fast does someone outside the train see the ball moving? We want to know, how do we do relativistic kinematics? How do we do these relativistic transforms for speed? And then we'll get into what's called four vectors, which is, let's now more formally get into redefining physics under these relativistic rules. So forces, how do they work? If we have forces and velocities and things like this, that means we have vectors. And now that time seems to be its own thing, it's not some fundamental thing in the universe, but rather it's kind of part of the material. It's just as much of a material of space as the x direction is. So instead of having 3 dimensions, x, y, and z, we have to add in a 4th dimension, time, and create our new vectors out of this 4-dimensional vector instead of 3-dimensional vectors, and go from there. So that's what we'll do next time. For now, I hope this was useful. You see where this gamma, or 1 over gamma, that's gamma itself, 1 over that, comes from, how it was derived, and all of that. So we'll get into some examples, see how to actually make calculations, and then once that's done, we will be able to get into the particle physics. So until next time, I will see you later.